for coming. This is really a very beautiful lecture hall, and the weather is actually relatively nice. I think it's almost as blue as it can be December in Erlangen. So it's a great opportunity to have today two speakers. Actually, both of them, Denisa Martinova and Giovanni Fantuzzi. They are members of our MoD Center that gathers also a group of junior professors of our university. The first lecture will be delivered by Giovanni. Giovanni came to our group a couple of years ago, no? 2, 3?
2022, 3 and a bit.
Yeah, okay, so 3 years ago. So he came as a W1, as you know, in the international terminology, this will be something like an assistant professor, right? He has been doing a great work in different areas. Before he got a PhD in Imperial College, he was also a postdoc in Oxford. His PhD in Imperial College was in the Department of Aeronautics, so he has a very interesting multidisciplinary profile, mastering different aspects of applied math and data science. And today he is lecturing on Lyapunov meets Koopman, a new approach to data-driven analysis of nonlinear dynamics, which is, as you know, an extremely hot topic right
now. Thanks, Enrique, for the introduction. Thanks for having me. Just for the record, I was in Oxford as a doctoral research assistant, not as a postdoc, but I was there for 6 months, nevertheless. So after writing the abstract and the title and looking at then how much time I had, I realized that maybe I promised a little bit too much. So I'll try to give you a glimpse of this new approach that I'm talking about, but then I will focus on a particular problem that you could study with this particular approach. But first things first, who are these two guys that I'm mentioning in the title? There's Lyapunov and there's Koopman. Hopefully you've heard of both of them. They're two guys that lived a century or more ago, but we still talk about them today. Lyapunov, the guy on the left, is pretty famous for Lyapunov functions, of course, and these are the tools that you use to study ordinary differential equations. So dynamical systems with a known ODE model, dx by dt equals f of x, f is a vector field, x is a vector in some d-dimensional space. You start this ordinary differential equation with an initial condition, x at time 0 is some point x0, and then your dynamics will evolve, right? So you could think of this x as being the position of a point, it will move in space, and it will do some crazy thing according to this law. And these Lyapunov functions were originally introduced to study stability of equilibria, right? So if you have a point that doesn't move, if you perturb it a little bit, will you go back to it? So that's a stability question. But actually, it turns out that you can do a lot more with variations of Lyapunov functions. So for instance, you can approximate absorbing sets. So sets in your space that are nice and compact, closed, bounded, and no matter where you start, where you put your x0, you will eventually enter this set and remain there forever. They're also called trapping regions. You can also, if you have an equilibrium, you can use Lyapunov function to approximate Bayesians of attractions. Or if your equations support chaotic dynamics, think of the weather, or think of any complicated engineering system that evolves in a complicated way in time, you could ask, well, what's the average power that my engineering system is going to consume? What's the average temperature that is going to be in Erlangen over a long time? Well, why? Because I want to know whether to buy a thick jacket or a t-shirt with short sleeves. Right, so you can estimate infinite time average. You can use Lyapunov function to design optimal controllers, and you can do a lot more. It just didn't fit on the slide. The key object that appears in all of these applications that I will not describe in detail is this guy over here, which is this mathematical object, f dotted with the gradient of a function v. F is the vector field of your ODE, and v is the Lyapunov function. It's a function that you're allowed to prescribe, and you have to choose it in the right way in order to answer the dynamical question that you care about. So f is, in this case, the model. It's known. You're looking for the v. This object will appear in a bunch of conditions. I will show you an example in a couple of slides. And if you can satisfy those conditions where this object appears, then you have an answer to your dynamical question, be it stability, be it time averages, being absorbing set, being optimal control, and so on and so forth. All right, so this is model-based analysis. Who's the other guy? Well, Koopman is the guy who somehow introduced something called the Koopman operator, which is something very famous. And the idea is to change perspective. So Lyapunov, you have an ordinary differential equation that takes a point and moves the point according to this nonlinear differential equation. Koopman said, let's change perspective. I'm going to take a function v, and I'm going to push forward through the dynamics. So the phi that you see here, you compose your function v with the flow of the ODE. Phi is essentially a function that says, if you start at this point, after a time t, you end up at a different point by solving this ODE on the right, on my right, on your left. Okay, so the idea is that by shifting from nonlinear dynamics of points to somehow dynamics of functions, you go from a nonlinear description to a linear one. The price you pay is that you have a nice point with maybe 2, 3, 4, 100 dimension, by finite dimension, to dynamics of functions, which are infinite dimensional spaces. So there's a nice linear perspective of nonlinear dynamics. More recently, this Koopman operator has become very popular because you can approximate it from data. And it just do some Galerkin approximation. I will describe it in a couple of slides, but essentially you just fit some model to this Koopman operator. And this makes it very popular. People have studied the spectral properties of this Koopman operator because it's linear. So when you have a linear operator, people immediately jump at it and say, aha, I can look at the spectrum and look at eigenfunctions if I can, and try to do spectral analysis of that. And you can use it to learn models, because if you believe that this Koopman operator is predicting what the function v looks like in time, if your function v is just the first state, the second state, and you plug in every single state of your dynamical system, well, then this Koopman operator is predicting the evolution of your states, and therefore is giving you the dynamical model, right? So this is the standard perspective that people have taken in the Koopman operator community. And when you look at these two things, they seem distinct. What I'm proposing in this talk is to make a change of perspective and actually say, let's forget about this linear operator spectral analysis and doing modeling from data just in the Koopman world. Instead, I want to draw a connection between these two sides of the slide. And the connection is that the key object for Lyapunov, this f.grad v object, this guy here, is precisely what you get if you apply the Koopman operator at some time t to a function v, to the same function v. You subtract v, you divide by t, and you let t go to 0. So you're somehow doing a time derivative, right? So the guy on the right is the time derivative of the function v as the system evolves. And if you do this operation, the f.grad v, which is the guy that appears in all of the Lyapunov theory, is the rate of change of v. So it's telling you information of how v changes. And you could already believe that if you can say something about how this function v changes in time, then you can say something about the dynamics. And that's the whole point of Lyapunov theory. Build a function v that tells you for which you can say something about its evolution, and conclude something about the dynamics of the system. Once you made this connection, which I'm not the one who's made this connection, this is some sort of simple basic math definitions, but what seemed to be missing from the literature is the fact that, well, now that I have this connection, I can approximate these so-called Koopman generators because you're taking a derivative, from data using the same techniques that you can use to approximate the Koopman operator. In particular, if you believe that you can approximate the Koopman operator here from data, then you fix a small t, and then you approximate the limit by a finite difference formula, then you get an approximation for this guy. And once you have an approximation for this guy without knowing the model, the ODE, f, then you can take the approximation and plug it into the Lyapunov frameworks and do data-driven analysis of dynamical systems. And you can answer a whole range of questions. So this is the new perspective in nonlinear system analysis that I was talking about in the title of my slide. Forget about spectral analysis of Koopman operators and all of that and the linearity and modeling directly from data. Use this simple connection so that if you want to do system analysis, you don't have to reinvent the wheel, meaning all of the model-based Lyapunov technology that we already have. We can just do a simple data-driven approximation of this object, this Koopman generator, plug it in, and run exactly the same analysis frameworks. And I think this is a pretty simple but potentially quite powerful observation. The rest of the talk, I want to focus on one particular question, which is this absorbing set approximation, just to keep things concrete. And in fact, I'm going to give a talk within a talk, and the title of this mini talk inside my talk is Learning Polynomial ODE Models with Boundedness Guarantees. So this is work that we just recently started with Albert, who is sitting here in some row there. And this is very recent, the stuff that we've done in the last 2 weeks. The idea is you get data and you want to fit a model to your data, but you want your model to not blow up to infinity, right? So more precisely, suppose that I have the dynamics of a certain point here and I start my simulation and this point will move. So this is truth. So I come along after a while and I start collecting measurements. These are my blue points. I collect them at a certain rate. My measurement device is maybe a little bit slow and it's a little bit noisy. So my measurements are not precisely on the black line, which is the ground truth, but there's some noise. Okay, so this is what I know, and then the problem is, given these noisy measurements at a fixed sampling rate, I want to learn an ODE, and I will learn it with a polynomial vector field F, for reasons that I will explain in a second, polynomial, for the dynamics. And I would like my model not only to do a good job at replicating the dynamics that I've seen in my measurements, I would also like that my model has a compact absorbing set. That means a green region in space, which is bounded, right? And this region should be such that no matter where I start my model, even if I start it over here, eventually I will enter and never leave again. Okay, so here I'm showing the ground truth that sat behind my simulation, plus a true absorbing set. And the point is that if you look carefully at the picture, you see that these vector field lines somehow are crossing the boundary of this green line. This is how you determine it. So why is this important? Because you have a certifiably well-posed model, right? You have some data, you've observed something that you want to make prediction in a different regime. You don't want your model to predict explosions, unless you're trying to build a bomb. But I suspect that most of us are not trying to build a bomb here. Okay, so this is the problem. How are we going to do it? Well, the first thing is to recall what Lyapunov taught us, or variations of the Lyapunov function. So it turns out that you can build absorbing sets using Lyapunov functions. All you need to do is you need to find a function v of x is my state, and a constant c that satisfies two inequalities. The first one is essentially telling you that your v blows up at infinity. It's coercive. The second condition is a complicated mathematical way of saying that if v becomes large as your system evolves, in particular if it becomes bigger than this constant c, then it will decay again. So the intuitive meaning of these two conditions is that if your particle, if your point x is trying to go to infinity, then v acts like an energy potential, and if the energy gets too big, then your point is going to turn around and come back. And therefore, it's not going to go to infinity. In particular, the set of points where v is less than c becomes the absorbing set. And this is precisely how I generated the picture in the first slide. So now I'm going to put some math to it to explain how on earth do you even construct this v. So the idea is the following. Here's the ground truth. My model is a two-dimensional ODE with a cubic nonlinearity. All right, here there's some cubic terms. I'm claiming that so the picture that I showed you has c equals 34, and v, which is the norm of x squared, x1 squared plus x2 squared, plus this crazy expression of degree 4. Right? So I'm claiming that if you take these guys and you plug it in here, the inequalities hold. Now you might think, how on earth did you do that? Right? And that's a good question. It's not obvious to find this v and not obvious to check that I work, even if I give them to you. So how did I do that? So for instance, let's check the first inequality here. Right? So if I rearrange, I bring the norm on the left-hand side, what I want to show is that 0 is less than or equal to this crazy expression here. And you look at it and you already think, well, this is not obvious, right? Because, yeah, this is a nice and positive guy because it's a power 4, and this also, but these guys, I don't know anything about. They could be positive, they could be negative. And it's not clear who wins. Now, if I told you that I can rewrite that guy in this complicated way that has a positive constant times a square plus another positive constant times another complicated thing square, then I have a sum of squares. Squares are non-negative. Therefore, everything is non-negative. The cool thing is that you can look for these sums of squares representation of polynomials using a computer. So I didn't come up with this by hand. I asked the computer to find it for me. And then I looked at the numbers that the computer was spitting out, and I realized that a number was 3 minus root 2 over 4. So you can sort of copy by hand what the computer is doing. And this is how I'm going to enforce these inequalities on a computer. I will ask the computer to look for sums of squares decompositions, and this is why I look for polynomial models, because the sums of squares techniques work with polynomials, roughly speaking. So there's a lot of technology that is sitting behind here. I just wanted to show you why these sums of squares techniques are important. OK, so now that I have this, how would I learn a model with a bounded absorbing set in a naive way? So I take my state measurements, y, my noisy state measurements, and I do a finite difference formula to get approximations, I call them fk, of the vector field. This is the time derivative. So these are, I just fit. And I'm not doing anything fancy. There's noise. I'm differentiating noisy measurements, so you should already be screaming, what the hell are you doing? But never mind, I'm just going to do this, right? Now I get some approximate measurements for my velocity field, for the ODE. So what can I do? Well, fit a model F, polynomial, that matches the measurements at the data points in a mean squared way. And I want my model F to have a Lyapunov function and a finite constant C that will create this trapping region. Right? So I could potentially pose this optimization problem. I'm looking for the F, I'm looking for the V, and I'm looking for the C. And I'm imposing the inequalities of these polynomials being non-negative by asking that they are sums of squares, because it's what the computer can do. Okay? So it turns out that you can't solve the problem like that, because you have to specify what degree these polynomials have. So you have to prescribe parameters. This is a choice that you have to make in advance, because you can't work with infinitely many variables in your polynomials. And there's related work that essentially gets to close to these formulations, but not quite. So on the one hand, there's work by Koopman-Lyapunov and others, and there's many other similar work, where they fit quadratic models. So f is a quadratic polynomial, and the v function that gives you the trapping region is a quadratic polynomial. So you're sort of looking for quadratic polynomials where the absorbing region is a ball or an ellipsoid. This is already quite restrictive, but worse, what they do is they never enforce the constraints exactly. They somehow penalize them in the cost. So once you've learned the model, you actually don't know whether the coercivity and the Lyapunov conditions here are actually satisfied. So you learn a model, and then you have to cross your fingers that actually it does have a trapping region. So there's no guarantee. On the other hand, there's other work that learns polynomial f, which is what I want to do, imposes the constraints, but they say, no, you need to give me the v beforehand. Why? Well, because there's a product here, and if I recall my optimization class, I recall that convex optimization problems are easy in general, and non-convex ones are hard, and this product is non-convex, so it's going to be hard to look for the f and the v at the same time. So they say, well, give me a v, then I can fit an f that has a trapping region described by that v. Problem, how do you come up with that v in the first place? And what if you come up with a bad guess? Well, then you learn a stable model, but if you have a bad v, then you have to pay in the cost, and maybe your model is not accurate. Right? So to get around this, I go the Koopman-inspired way, because I realize that this guy, which is where the difficulty arises, is precisely the Koopman generator. It's the thing that I can approximate from data using this Koopman theory. So I propose this very simple change, just putting a step 1.5, where we approximate this object that is the difficult one from data. So I want to explain a little bit how I do that and how much time do I have, maybe 10 minutes. So we should be on track. There's a little bit more math in the coming slide, so please bear with me, and then we see examples. So how would I do this? Well, I know that I want my v to be a polynomial. So I will expand it with some polynomial basis. You should think of these phi i's to be the monomials, like 1x, x squared, x cubed, and so on. But for numerical reasons, you might want to use Chebyshev polynomials or another polynomial basis that you like. So that's why I use the generic phi. And what you want to do is to tune the a's, the coefficients of your polynomial. Okay? So if I want to approximate f dot grad v, well, really, I need to approximate f dot grad of the basis functions, or the phi's. So these are the guys that I really need to approximate from data. What do? I'm going to fit a polynomial wi to it. How? Solve a least squares problem. I have my approximate f. I know my measurement y. I plug it in, and I want to construct a polynomial w that approximates it. As simple as that. This is the essence of these extended dynamic mode decomposition Koopman approximation methods. Least squares fitting of a polynomial. There's nothing more complicated than that. Of course, if you want to analyze convergence and prove theorems, then the more complicated theory is very useful, but in essence, you're just fitting a polynomial to data. So now that I have this w, which is an approximation of the guy that I want, I will look for my v by solving an optimization that looks like the following, and it looks complicated, but c is the constant that determines how big my trapping region is. And then the other two objects, the guys here in purple are just my function v. And these guys, where I don't know the a's but I know the w's, are just the approximation of the f dot grad v object. And if you believe that I have enough data to get a good approximation, then the solution of this problem should give a good v for my system. And the crucial thing is that I've learned this v just based on the data. I never needed to know the f. I only have measurements, approximate measurements, noisy measurements. Still, I can learn a v function that should know something about my system, and then I can hope to use it in the model discovery business exactly like in the previous work. Yep?
Why don't you optimize directly this difference? So you could also say just optimize the difference between the red and the orange one, right? And not distinguish the C. So why did you impose the
Because,
AI that this is optimized now?
good question, because what I want to do is you could have a problem where, yes, I can find AIs, easy to make this positive, drive C to plus infinity. But then the trapping region becomes the whole space, which is not a trapping region. But I want a finite trapping region, so I want C to be finite. That's why I want to make sure that my C doesn't explode, so I'm looking for some finite C. And then I'm trying to look for the V that works. And in the W's are fixed beforehand.
Yes, but I still did not get it. Why? So you want to find A such that those A approximate, so that this thing you mark as V approximates this F?
Yep. Well, no. The F I've approximated beforehand.
Okay.
Now I'm looking for the A's, meaning I'm looking for my Lyapunov function that should give me a nice bounded region where I believe that my system remains. So this step is just, I'm building my Lyapunov function, I'm building the green trapping region. I haven't built a model yet, not explicitly at least. This comes next. Once I have the V, I can fit the model that has the prescribed trapping region. And that's what I do. Now we have convergence analysis for this step, for this approximation, but you might need a lot of data. So I might admit that this guy that I have is actually a bad approximation, so maybe I don't want to impose this constraint strongly, so I'll penalize it in the cost. What I'll do is I would like this guy to be equal to a sums of squares, so I call my sums of squares sigma, and I penalize the difference between the object that I want to be a sums of squares and indeed something that is sums of squares. So this is my way of admitting that this guy in this approximation could be quite bad. But this is not a problem, because this problem here still gives me a function V and a trapping region that knows something about my data. And then I can use this V to learn a bounded model. So this is what we do to generate this picture. So what you see on the left is the exact truth. What you see on the right is the trapping region that I learn by tuning these A's. And then the lines, the vector field, is the stable vector field that I've learned. I have 93 measurements, 93 data points, which is not a lot when you think about it. And my polynomial degrees are 3, 4, and 6, which are just the right ones for this example, so it's not surprising that it works. So this is the first iteration, but now that I have a model, I could say, okay, I have a model, find the best trapping region. You see the green region on the right is quite loose, but you could optimize it, and if you optimize it, actually my model has this trapping region. And if you look at the two pictures, they already look quite similar, except for maybe the stuff that goes on inside here. Now that I have a new trapping region, I can try to re-optimize my model, so I can start iterating in an alternating fashion. So the second iteration, I learn this model with the old trapping region. And then I can re-optimize the trapping region and make it tight. And if you look at these two pictures, they look very much the same, right? I know that to generate the one on the right, I knew nothing other than the data, the blue points. And then I can keep iterating until I converge, and you will see that iteration 4 and 5, nothing changes, right? So somehow I converge, and I do very well. So I think this is pretty good, and compared to previous work, I have guarantees that wherever I start my model simulation, even if I start it up here, eventually I will end up in the green region. Mathematical proof. Okay, you might think, yeah, this is great, but you chose right the parameters and the polynomial degrees that were exactly the one for the true model, but what if you didn't know it, right? Well, okay, let me try a more complicated model with higher degree, right? So now instead of my truth is an f of degree 3, I try degree 6. Well, I learned this model, right? It's topologically different, right? It's a different trapping region, but actually if you look close to the data, the vector field suggests that you're following this line, which is exactly what the data is doing here. And of course, if you only have data in some region of space, why should you expect to do a very good job far away from the region where you've collected data, right? So I've learned a system of degree 6, which models my data well and is bounded. And there's no reason to hope that or believe that far away from the data, it should behave exactly the way as the truth. All right, so what happens if you increase the number of data points while the picture remains kind of the same? Nothing changes. What happens if instead of looking for a V that at degree 4, like the analytical one, I look for a V that has degree 2? Like previous work say, no, just put a ball, right? I like balls, they're simple. So that means a Lyapunov function of degree 2. Well, this is quite a funny exercise because the ground truth, you can prove that there is no trapping ball, no trapping ellipsoid. You try and prove that the system on the left here is bounded using a ball or an ellipsoid, you fail. You need to use degree 4 to prove that it is bounded. But on the right, I succeed, and you see that everything looks green, but this is because if I zoom out, there is a bigger ball. Right? The previous picture was the red square. I still learn a system, and this is because in the data-driven world, I get away with slightly changing my system to make a ball work. I pay a little bit in accuracy in the data, in how I represent the data. What happens if you try to fit a quadratic model with an absorbing ball or ellipsoid, to this case, which is the majority of the work that is out there? You fail spectacularly. You learn a system that collapses to the origin, or to an equilibrium point close to the origin. You certainly do not mimic this limit cycle behavior that the data has. So this extension that I'm proposing, despite being quite simple, is actually pretty powerful and necessary in these examples. All right, one more example. What happens if my original truth is not polynomial? After all, I was learning a polynomial model with a polynomial, so of course you might expect it to work. So here's a chaotic system in 3D. It's called the Thomas system. It has some sinusoidal terms in there, right? I ran the whole procedure, and I learned this very complicated model. Is it learning roughly the same thing? So if you look at these orange terms, maybe you recognize that here in my model somehow captures these guys. It's not quite 0.2 the coefficients, but I have 6% noise, which is quite a lot. And then you wonder, well, what's the rest? Then you realize, you recall calculus, and you say, I learned about Taylor expansions, so let me Taylor expand the signs, and you get these sort of expansions. And if you look closely, and you allow for a little bit of numerical inaccuracy, you realize that you see those terms. So I'm actually learning a Taylor expansion of the sign. What's the rest? I don't know. I don't care. It's not going to cause instabilities. I have mathematical proof of that, right? So this is precisely the problem of this. If you didn't have these guarantees, all of these extra terms that you might learn, and you don't know what they are, often cause instability. As you start your model from a different initial condition, the simulation will blow up. In my framework, and in the framework that I'm developing with Albert, in fact, this is proven not to be the case. It's guaranteed to work. And I think this is pretty powerful, just by a simple change in perspective. Okay, further perspectives and quick conclusions and open question, and then I'll stop. Apologies for going a minute or two over time. So it turns out that the same ideas, as I mentioned at the beginning, using this Koopman-inspired data-driven approximation of the objects that appear in the Lyapunov conditions, can be applied to a lot of other problems, like estimating peak values of some observable, some quantity that you care about, like energy, power consumptions, deformation on an attractor, right? Why would you want to do that? Well, suppose you're flying a plane to the next conference that you're going to, and you hit some turbulence. The wings of the plane will start to vibrate, right? Well, there's complicated interaction with the air and the structural dynamics. You would very much want to know that your wing is not going to suddenly flap up and break, right? That the deformation is below some value. The model is complicated, but you can collect data of how the wing is moving, and then maybe you can do data-driven analysis of peak behavior. And then you could do time averages. You could discover invariant measures and so on and so forth. You could also do stochastic dynamics. I haven't talked about stochastic dynamical systems, but you can extend these Lyapunov frameworks to stochastic differential equations, stochastic maps. You can use the same ideas and the same data-driven approximation in the stochastic setting. Fun fact, the expression of the generator comes out automatically. You don't need to prescribe what the generator would look like. If the system is stochastic, these data-driven approximation methods will automatically pick it out for you, which I think is pretty cool. Okay, open questions. There's question of practice, making it scale. The problem is that I'm using the sums of squares technology to enforce the Lyapunov conditions. They don't scale too well. So if you want to learn models with like 5, 10 states, then sure, you can probably do it. But if you want your reduced order model to have 100 or 200 states, because you're trying to take a big PD discretization, which has millions of degrees of freedom, and boil it down to a few hundreds, well, that's more difficult. So a good question is, can we couple this with encoder, autoencoder, encoder, decoder structures from data? And are there any good applications while learning these models with stability guarantees would be very, very useful. So these are questions for practice, and I'm happy to hear if you have suggestions. And then from theory, well, I mentioned some convergence analysis. There's more to be done there, proving error bounds, telling me if you have this much data, your estimates based on these data-driven Lyapunov frameworks have this much error, so you're this much far from the truth. This remains to be done. And there's some non-trivial math because you're combining 3 fields which have largely been developed independently, and one is to figure out how they fit together. So if you're interested, I'm happy to talk to you. With that, I'll stop. Apologies for going a few minutes over time. You can contact me. I have an office here, obviously. Reach me by email, and if you want to know more, there's a couple of papers already on this subject, so feel free to have a look at those. Thanks.